Yeah, so hello everyone. Welcome to my last lecture of this class. You'll have one more from Ethan, but this is it for me. Um, and so before we get into today's lecture, um, I just want to take a little bit of time to appreciate just how far we've come. In lecture one, we defined a vector as a list of numbers. We then learned that we can add these lists, we can scale these lists, we can multiply these lists in strange ways to get back numbers. We talked about Graham-Schmidt, perhaps too much. We talked about how to transform these vectors using this class of functions called linear transformations. We've talked about how to represent those linear transformations as matrices and the interchange between matrices and linear transformations. We showed how you can use matrices to solve linear systems. We talked about the null space problem, the eigenvalue problem, and finally we've talked a little bit about affine geometry. And that's actually quite a bit. Thinking back to like week one versus now, like the amount of stuff we've covered is quite large. And I am really grateful for everyone who has been along for this ride, and I hope it's as useful to you as it was for me when I learned it. I would say that linear algebra was the class that made me go from liking math to loving math. And so I hope that this class has imparted at least some of that to all of you. So thank you for all joining in on this class. We're going to talk today about rotations, specifically rotations in 3 dimensions, but we'll touch on some general theory of rotations. And these kind of have a special place in my heart because rotations, I would say, was the thing that really inspired me to want to teach a class like this in a funny sort of way. So let's get into it a little bit. We have told you that rotations are linear transformations. We have perhaps justified this a little bit, but we have not really proven this in any meaningful way. So my first goal is not actually to do a rigorous formal proof, but to justify why rotations are linear transformations. Oh, I am not sharing my screen, thank you. Though I'm not writing anything right now either, so you haven't missed. What I wrote was rotations, but I wrote that before we started. So I want to justify to you, and actually prove but not rigorously prove, why rotations are linear transformations. So I want to first start out in 2 dimensions. So in 2 dimensions, also I'm actually going to be writing with my mouse today. Ooh, that's not what I wanted to do. So you'll get to see my epic mouse writing skills. In 2 dimensions, we have these 2 standard basis vectors, 1, 0 and 0, 1, right? And we've gone over how you can uniquely define a linear transformation by knowing where it maps the standard basis. So let's think about this really quickly, right? We've got this 2-dimensional grid. We have 1, 0 here. We've got 0, 1 here, right? Now, if I think about a rotation, right? In 2 dimensions, a rotation can do 2 things. It can rotate us counterclockwise, or it can rotate us clockwise, right? So let's say I want to rotate by some number of degrees that we'll call theta. And it's going to be, this angle here is going to be theta degrees. Right, and let's say I'm rotating counterclockwise, because we like rotating counterclockwise. You can do the math, you can figure it out. What this will do is it will send this first standard basis vector to, if you don't mind my brief trigonometry lesson, if you make this little triangle here, you get a triangle like this. And if you don't know any trigonometry, that's totally fine. It's just for the people who do know the trigonometry. Right, this is here. This hypotenuse is going to be 1. And so the y value is going to be sine theta. This x value is going to be cosine theta. So it's going to send this first standard basis vector E1 is going to be sent to cosine theta, cos theta, sine theta, right? And E2 is going to be sent to a very similar thing. It goes like this by an angle of theta itself. Let's see, cos theta, sine theta. I'm just going to write out the matrix because it helps me remember. This gets sent to negative sine theta. Boop, 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 cosine theta. Yeah. Okay. So I think I wrote this. I believe I wrote this formula previously. So the rotation matrix for 2 dimensions is going to end up looking like this. Look at cos theta, sine theta, negative sine theta, cosine theta. But again, I haven't really justified to you why this is a linear transformation, right? So, if I know that my function is a linear transformation, then I can write it as a matrix using the trick I just used. If I huh. No, it's not just you. That was me. That was my brain cutting out briefly, because I may have made a mistake. No. Anyway, sorry. Oftentimes people write this matrix as a clockwise rotation, which annoys me, but also means that makes the signs different. Anyway, so right, I haven't justified to you that this is a linear transformation. And again, I'm not going to formally prove that rotations are linear transformations, but I want to justify that it is. So first of all, the fact that these 2 vectors map here is true, right? So as soon as we prove that this is a linear transformation, we can use our formula for computing a matrix of a linear transformation and get that this column should be this vector, and this second column should be this second vector. So let's think about what properties rotations have. Well, the first thing, and this might sound a little bit weird, is this notion of angle preservation. So what do I mean by that? Well, imagine I had an L-shaped thing, right? In Roblox, you can imagine this being a part where I'd welded two rectangles together, right? Um, and this has a 90-degree angle. Well, if I rotate by some number of degrees, right? If I rotate this whole thing by some number of degrees, this angle between these two lines shouldn't change, right? Even after rotating my part, the angle here should still be 90 degrees. And so what this actually gives us is like part of this actually gives us linearity. It gives us that this is a linear transformation, which might seem weird, but let's say, right, that I want to compute where this vector ends up, right? Well, I can just add on, the basis vector 1, 0, right? And I can imagine gluing these two parts together to make this little wedge-shaped thing with a certain angle. And so when I move 1, 0 to wherever it ends up, it might end up, I have to get another color, if 1, 0 ends up here, then the other vector's got to end up here, and this angle has got to be the same as it was here. You get some nice star-colored stuff. And so you actually, as long as you know where this first standard basis vector mapped, you actually can figure out where the other vectors mapped. And this idea that as long as you know where the basis goes, you know where everything goes, is kind of the core idea of linear transformations. So again, this isn't like a proof or anything. It's just kind of the reason we might expect that these things work. Unfortunately, this intuition begins to fail for 3 dimensions. And so I am going to ask you kindly to blindly follow me into the abyss of 3-dimensional rotations, because 3-dimensional rotations are fundamentally very weird. So instead of trying to define them intuitively, I think it's probably, I am at least going to take the approach of trying to define them mathematically as the primary method. So let's think again about this property. Actually, first, are there any questions about what I said so far? I'm not sure if this was super useful. This was useful to me when I was thinking about it. Right, it's like the idea that if you know where E1 ends up, you can figure out the same thing. Actually, no. If we lived in 4 dimensions, this would be a much easier class. 4-dimensional rotation is not weird. Another way to think about this is that if you look at this displacement vector, the displacement vector is between these two things. So I can add the exact same displacement vector. Oh, I say it's been rotated. Sorry, but it's the same size. Because we preserved the angle, this displacement vector has just been rotated, but it should remain the same size. So we can just, as long as you know where E1 ended up, we can just add the displacement vector. Yes. So yes. Anyway. So I want to go back to 3 dimensions, and I hope you'll take my word that rotations are linear transformations. That is not how you spell rotations, but I will keep going. Are linear, which means we can basically just talk about linear transformations and try and figure out what properties rotation should have. So like in 2 dimensions, the property that I mentioned that was really important was this angle preservation property, right? If I take 2 things and I weld them together and then I rotate them together, the angle between them should be preserved. These angles should be the same if I rotate the object. Now in 3 dimensions, we still want this property, right? So we want a linear transformation that has this angle preserving property. Now, as I've mentioned, linear transformations are uniquely defined by their value on this standard basis, which in 3 dimensions is going to be this basis here. Right, so as long as we preserve angles for these 3, we're good. So what does that all mean in concrete steps? Well, if I may try and visualize something here, you can think of, that is not what I wanted, but I'll run with it. You can think of this as being E1, this as being E2, this as being E3, right? And they're all at 90 degrees from each other. Well, what does it mean for the a linear transformation here to be angle preserving? Well, we have a name for when a list of vectors are all at 90 degrees from each other. And that name is orthogonality, right? So the fact that E1, E2, and orthogonal just comes from the fact that, like 1, 0, 0, inner product with 0, 1, 0, right? This is going to be 0 plus 0 plus 0, which is 0, right? So they're all orthogonal. And so really all we need is to guarantee that these 3 basis vectors will all map to a set of 3 other vectors that are all going to be orthogonal. So, we have this set of vectors here. That is not what I wanted to do. And when we map it with our linear transformation, I'm going to call T, it needs to map to some other list of vectors that are all also at 90 degrees from each other. Right? And that makes sense, I think, because if you take a square, right, and you rotate it, or if you take a cube and rotate it, it shouldn't stop being a cube. If you don't have this angle preservation property, you're saying that when you rotate a cube, it can become like a parallelogram or like a weird skew object, right? And this doesn't conform to reality, right? If you take a cube in 3-dimensional space, like yourself, and you rotate it, it doesn't suddenly become not a cube. It's just a cube in a different orientation. So to guarantee this fact, we just need to make sure that our E1, E2, and E3 map to vectors that are also all at 90-degree angles from each other, right? Are there any questions about why we need this? Again, like my way of thinking about it is like, yeah, you say like this can be thought of as the corner of a cube. How does the angles preserved between rotations show linearity? That's a great question. The answer is that you should think about it. I could go into a proof, but I don't think I have the time, unfortunately. We can talk about it in office hours. But the kind of thing to think of is like when you do like vectors geometrically, when you have Ethan likes to draw these diagrams where you have like one vector being added to another vector. If I take this whole thing and I rotate it, does it really matter that I rotated it? The resulting vector also got rotated. I rotated each vector, but the resulting vector also got rotated. And so, if you think about this as being a displacement, and this as being the two vectors with the angle between them, right? If I rotate this whole assembly, unfortunately I can't rotate it about a specific point, but if I rotate this whole assembly, right, it doesn't. The addition still remains, right? The fact that these two vectors, let's say 1 and 2, these two vectors add to the third vector has not changed by me rotating this whole assembly. Does that make sense? Does that help at all? Okay. But if you believe me that rotations are linear, then we can work out what algebraic properties they should have. And the first one is that it needs to map this standard basis to a bunch of orthogonal vectors, right? So, if I have this a linear transformation T, it should map E1 to some vector R1. It should map E2 to some vector R2. It should map E3 to some vector R3, such that R1, it looks like a 2, so I'll roll with it. R2 inner product R3 equals 0. R2 inner product R1 equals 0. And R1 inner product R3. And this is that angle preservation property. Because again, if you rotate a cube, the cube does not stop being a cube. Now, so let's write this as a matrix, right? So we've talked about how to write a matrix as a bunch of columns. Say this matrix R1, R2, and R3, right? So what other properties should rotation have? Well, crucially, rotation also doesn't scale things, right? To go back to the cube analogy, right? If I rotate a cube, it does not become bigger, right? Like when we're defining what a rotation should do, we're basically trying to have it match reality. So if I rotate a cube, the cube should not get bigger, right? So in fact, each of these resulting vectors here, these each need to also have norm 1, right? Because if we take the length of E1, this is 1. And so because our linear transformation isn't scaling anything, isn't making anything longer, we also must have that the length of R1 is 1. And similarly for R2 and R3. So these are all going to be orthogonal vectors with norm 1. And we have a name for this. Particularly, it's called being orthonormal. So the first condition for being a rotation matrix is that your columns must all be orthonormal. Does that make sense? So orthonormality is baking in as one thing the fact that our linear transformation doesn't make anything longer or shorter, and also baking in the fact that it preserves angles, right? And so what you can think about this is like we have our 3 vectors E1 through E3, almost 3 straight vectors, and they are going to map to another set of vectors that are also orthogonal to each other. But they might be in a different orientation. That's an arrow. But they're also all going to have length 1. right? So they're all the same length. Does that make any sense to people? One way to do it is like if you put your hand like you were doing the right hand rule, and you move your hand, you rotate your hand, your fingers don't get longer, right? If they did, this would be medically problematic. And also, as long as you don't move your fingers relative to each other, they're also all going to stay at 90 degrees from each other, right? So if you have your fingers like this and you rotate them, nothing's changing, nothing's getting longer. All the angles will stay the same. The rotation does not affect them at all. So this is like the first two properties of rotations that we should have. And I hope those are somewhat intuitive. Like, rotations don't make things longer, and they should keep 90-degree angles at 90 degrees. I see Borb is typing, so I want to wait. So the fact that rotations don't make things longer doesn't mean if rotations made things longer, they would still be linear transformations. Because linear transformations can make things longer, but they wouldn't be rotations anymore, right? It's the fact that rotating things doesn't make things longer, not that linear transformations can't make things longer, right? Because if I take, for instance, the matrix 2, 2, 2 with zeros everywhere else, this is just going to make everything 2 times bigger. So it'll just take a vector like this, and it'll send it to a vector like this, right? So this isn't a rotation. It does preserve angles, so it's almost a rotation, but it makes things longer, so it's not a rotation. In fact, this brings up a good point. The identity matrix is technically a rotation. It's the rotation of doing nothing, right? Like, you're always allowed to rotate 0 degrees. But that's just a funny thing to note. So this orthonormality property, though, is like really important. But it turns out to be very easy to express. Because let's think about this matrix, right? It's got these columns, R1 through R3. By the way, this orthonormality property should hold for any rotation matrix in any dimension, but we're only talking about 3 dimensions right now. So let's actually multiply this matrix by its transpose. You'll get a matrix that looks like this, where the rows have been put on their side, right? And if you do a little bit of algebra, you'll actually find out that this matrix is the matrix of inner products of the vectors. This is going to be R1, R2. This is going to be R1, R3. And I'll keep writing this as I'm talking, because every I have I have transposed this, but actually it's symmetric, so it doesn't matter. So so this matrix of every professor who teaches linear algebra is required to write it out at least once. So you should perhaps notice something about this matrix. If we assume that all of these column vectors are orthonormal, then we'll get the following interesting result. On the diagonal, this, for instance, R1, inner product R1, well, this is the norm squared of R1 by definition, because the norm of R1 is the square root of this value. But this is by definition 1, right? So it turns out that the diagonal of this matrix is just 1. But each of these off-diagonal inner products, well, those also can be calculated very easily because we're assuming that our vectors are orthogonal. So the off-diagonals have all got to be 0, right? So it turns out that this matrix times its transpose is actually equal to I3, the 3 by 3 identity matrix. And you actually can do this in reverse. If we don't start by assuming that these are orthogonal to each other or orthonormal, and we only start by assuming that this matrix here is equal to this identity matrix, well then, the norm of each of these vectors must be 1 because we have that this equals 1. And we also have that all the inner products between the vectors are also going to be 0. So just by stating that our matrix times its transpose is the identity, we've actually stated that this matrix has orthonormal columns. And so you will sometimes see this as Q transpose Q equals Q transpose equals I. And so this is the first really important idea of rotation matrices, which is that they are, quote, orthogonal matrices. So an orthogonal matrix is just any matrix that satisfies these properties. That itself, the matrix transpose times itself equals itself times itself transpose equals the identity. So this property here, this is called orthogonality for matrices. But you'll note that I didn't call these rotation matrices. I called them orthogonal matrices. So there's actually one more important property that rotation matrices have, which we haven't talked about yet. And it's a very subtle idea. But you've actually already potentially seen this in Ethan's collection of cursed things you can do with a C-frame. If I have, if I'm back in 2 dimensions, and I have a vector here and a vector here, and I rotate them, well, I'm rotating them counterclockwise. Let's say this one's like really much shorter than this one, to make it obvious. After rotating them, the short one should still be on the left of the long one, right? If we think in a counterclockwise rotation, right, the short one should still be like to the left of this one. And when I say to the left, I mean if I were to rotate this whole thing, right, you'll see, look, the short one is on the left of the long one. But as far as the linear transformation is concerned, a linear transformation could actually transform the vectors in a way where now the short one is on the right of the long one. That's possible. So in order to be a rotation matrix, we must destroy the possibility. We must completely get rid of this what's it called? Order reversing possibility. And it turns out we've actually already talked about the operation that we can use to figure this orientation reversing property out. And it starts with this note that, well, let's remember the determinant. The determinant has this interesting property which we talked about, which is that it's multiplicative. So the determinant of a product of two matrices is equal to the determinant of one matrix, the first matrix, times the determinant of the second matrix. Now, one thing I didn't tell you is that the determinant of the transpose should be equal to the determinant of the matrix itself. But also, more importantly right now, actually, no, let's start with something else. I forgot to mention one thing real quick, which is, okay, so I said that orthogonal matrices satisfy this Q transpose Q equals identity, right? This actually means that Q inverse is equal to Q transpose, right? Because the inverse of a matrix is just whatever matrix, when you multiply it, gives you the identity, right? But we've already found this matrix. It's just Q transpose. And so if we use this multiplicative property of the determinant, the determinant of both sides, the determinant of I is going to be 1, and the determinant here distributes. And so we actually get that the determinant of Q transpose times the determinant of Q is equal to 1. Okay. So why have I done all this? I claim, and we didn't prove this, unfortunately, that the determinant of the inverse of a matrix is going to be equal to 1 over the determinant of the matrix. But actually, I also have basically just proved this, right? If I divide the determinant on both sides, I'm going to get this exact thing for Q. So actually, let's just work with Q. Right? Q. Right. And so yeah. Okay, so we have this here real quick. Let's think about what the determinant of Q can be. Sorry, I went off script for a bit. So if you remember to my original description of the determinant is just the signed volume function, right? So it's just this signed volume of Q. But I've already said that the columns of Q are all orthogonal, and they're all length 1. So they're just going to make a box with side lengths all 1. Look at my terrible box drawing skills. These are all going to have side length 1. It's going to be a cube. So up to a sign, this determinant has got to be 1. So the determinant has got to be plus or minus 1. But from this equation up here, if the determinant of Q is 1, then the determinant of Q transpose is 1 over 1, which is 1. And if the determinant is negative 1, then we get negative 1 over 1 over negative 1, we get negative 1, right? So there's only 2 options for the determinant of Q. It can either be negative 1 or 1. and its inverse is going to have the same sign. That's all I wanted to say. So it turns out that this is kind of the distinction we want to make, which is that we want the determinant to only be 1 for a rotation. And so why is that? Well, we said that if you that like the determinant has this property, right, where if I have this matrix R1, R2, and R3, I have the determinant of this. If this is 1, then if I swap 2 of the columns, the determinant will become -1. And swapping the columns is exactly this thing we want to avoid, right, from our two-dimensional case, where we said, we want the small one to be on the left of the large vector here. Are there any questions about that? Okay. Okay. I have a feeling there's questions, but I know this is gonna be a lot to digest with the like whole determinant 1 thing. But this is like this is what we wanted. So, people have been asking, like, what can a C-frame do? So let's talk about that. Right. So the kind of big takeaway right now is that rotations. That is still not how you spell rotations. I don't know why I keep. Rotations are linear. They are orthogonal, which means that they are angle preserving and length preserving. And they are determinant 1. So these are the 3 properties that all rotations have. And so as a matrix, this ends up with this thing where we have a whole bunch of rows like this. Sorry, columns like this, I mean. We have a matrix Q that looks like this. If Q is a rotation, then we must have that Q transpose Q equals Q transpose equals the identity, and we must have that the determinant of Q is 1. And these are the properties that you must have to be a rotation. And so all that a C-frame is a C-frame, to go back to what we talked about last week, it's an affine transformation. So it can be written as a 4x4 matrix, and it's going to look like this. So every C-frame looks like this. So what does this mean? This upper thing is going to be a 3x3 rotation matrix. This here, this is just a vector. This is going to be our displacement vector. That's how I write my z's, as I've mentioned. This is just 0, as we talked about last week, because to be an affine transformation, this bottom row has to be 0, 0, 0, and then a 1. This is just 1. And so when you ask, like, it was asked last week, like, what can't you do with a C-frame? Well, at least unless you mess something up intentionally, um, the difference between a C-frame and a regular just any old affine transformation is that its linear part has to be a rotation matrix. So it can't stretch things, it can't make things longer or shorter. It has to preserve angles. It has to map things, any pair of angles that's at 90 degrees from each other has to remain at 90 degrees from each other. And those are the three properties it has to obey. So are there any questions about that? About like what a C-frame is doing and what restrictions are put on the matrix? All right. I guess I'll just leave you with one short tip for working with C-frames. So okay, so there's a question in chat about like the angle preserving with a C-frame. So I don't actually know much Roblox lingo, but yes, basically, if you have a part and you transform it by a C-frame, um, the up vector, the look vector, and the right vector should all remain at 90-degree angles from each other, right? If I'm correct, they started at 90 degrees from each other, and they should end at 90 degrees from each other, no matter what C-frame you apply. Now, I hope that helps. Um, so like, when you're working with a C-frame, right? I've said that if everything goes right, it should have this angle, all these three properties. One like word of warning: if you as Ethan showed in one of his demonstrations, maybe was it, or maybe it was during office hours. If you keep applying C-frames over and over again, you're going to end up building up this large product of orthogonal matrices. And a product of orthogonal matrices should remain orthogonal. And so a product of rotation matrices should remain rotation. But your computer is not perfect. Every time it multiplies these things, there's going to be a little bit of error. And that error can build up over time and cause your C-frame to actually stop being a proper C-frame. And so there is actually a function in Roblox called orthonormalize. Oh, so Armand mentioned this, which basically fixes this problem. It basically it uses not something. It uses something similar to Graham-Schmidt to basically force this product back to being orthonormal. So that's just a little thing. So yeah, that's 3D rotations. And it's a visual topic, so I think Ethan's lecture will be very, very good for visuals. But are there any questions about rotation matrices in general, especially 3D ones? The big three takeaways are these three things here. Like this is if you can get this, then you completely understand 3D rotations. Whoa. Okay, so I liked Borb's question, but I don't think it should go in the recording. So unless there are any other questions, I'll stop the recording and then I will try and answer Borb's question. Are there any other questions? All right. So I'll stop the recording.